Did you ever imagine the biggest explosion in the universe? Tonight, we slowly explore supernovas, the quiet, inevitable endings of massive stars. These immense cosmic events unfold after millions of years of balance, releasing light, energy, and the elements that shape galaxies and worlds. As you relax and drift deeper into rest, let this gentle journey through dying stars and vast cosmic time guide you towards sleep. Long before a star ever reaches its final moment, before light tears across space in a brilliant supernova, there is an immense period of calm. This calm is so long, so steady, that it is easy to forget it exists at all. Tonight we begin not with an explosion, but with stillness. Across the universe, stars spend nearly all of their existence in balance. They shine gently, holding themselves together through an unbroken agreement between two opposing forces. On one side, gravity pulls inward, endlessly trying to compress the star into something smaller, denser, quieter. On the other, nuclear fusion pushes outward, releasing energy from the star's core in the form of light and heat. As long as these two forces remain equal, the star remains stable. It glows, it endures. From a distance, stars may seem constant and unchanging. Night after night, they appear in the same positions with the same brightness, giving the illusion of permanence. But this is only because time in space moves differently than time in a human life. What looks eternal to us is, in truth, a slow process unfolding across millions or billions of years. Every star you see is alive in its own way. Not alive like a plant or an animal, but alive in the sense that it is active, evolving, and governed by a life cycle, with a beginning, a long middle, and an inevitable end. To understand supernovas, it is essential to first understand this long middle, the quiet majority of a star's life. Most stars are born from vast clouds of gas and dust, drifting through galaxies. These clouds, often stretching across hundreds of light years, are cold and dark, barely noticeable against the background of space. Over time, small disturbances, perhaps the shock wave from an ancient supernova or the gentle pull of nearby stars, cause parts of the cloud to collapse inward. As the gas compresses, gravity strengthens. The material falls inward more quickly, forming a dense core. Temperature rises, pressure increases. Eventually, the core becomes hot enough for nuclear fusion to begin. This moment marks the true birth of a star. Fusion begins when hydrogen atoms in the core are forced together under extreme heat and pressure. When they fuse, they form helium, releasing a small amount of energy in the process. That energy radiates outward, traveling from the core to the surface, and finally into space as light. For most stars, this hydrogen fusion phase lasts longer than any other stage of their existence. It is a period of remarkable stability. The star burns steadily, neither expanding nor collapsing, simply converting hydrogen into helium at a consistent pace. Our own sun is currently in this stage. It has been here for billions of years. It will remain here for billions more. During this time, stars are quiet. They do not explode. They do not dramatically change. They simply shine. But even in this calm phase, change is slowly taking place. Every moment a star shines, it consumes fuel. Hydrogen in the core gradually decreases as it is converted into helium. The balance between gravity and fusion remains, but the internal conditions are subtly shifting. The core becomes denser. Temperature creeps upward. Fusion reactions adjust to maintain equilibrium. This slow evolution is invisible from afar, yet it is relentless. Eventually, hydrogen in the core begins to run low. When this happens, the star does not immediately explode. There is no sudden catastrophe. Instead, the balance that held the star stable for so long begins to change, almost imperceptibly at first. With less hydrogen available for fusion, outward pressure weakens. Gravity gains a slight advantage and begins compressing the core further. As the core compresses, temperature rises again, igniting new reactions in surrounding layers. The star responds by changing shape. In many cases, it expands into a red giant or supergiant, growing enormously in size while cooling at the surface. From the outside, it may appear calm and majestic, swelling gently over millions of years. Inside, however, the conditions are becoming more extreme. Heavier elements begin to form. Helium fuses into carbon, carbon into oxygen, oxygen into neon, neon into silicon. Each step releases less energy than the last and requires higher temperatures to continue. The star must work harder and harder to support itself against gravity, yet still there is no explosion. The star remains, layer upon layer, like an onion of burning shells surrounding a dense core. Each layer fuses a different element. Each reaction pushes outward just enough to resist collapse. This phase can last for millions of years in smaller stars, or only thousands of years in the most massive ones. Time accelerates as the star approaches its final stage, though from a human perspective, it is still unimaginably long. At the center, something crucial is happening. Eventually, fusion produces iron. Iron is different from all the elements that came before it. While fusing lighter elements releases energy, fusing iron consumes energy. There is no longer any benefit, no outward pressure to be gained. The star cannot extract power from iron fusion. This is the turning point. When the core becomes dominated by iron, the star has reached the end of its ability to support itself through nuclear reactions. Outward pressure weakens rapidly. Gravity, patient and unyielding, takes control. The collapse begins, but even now the process is not instant. The core contracts, heating further, becoming unimaginably dense. Electrons are forced into protons, forming neutrons. Matter compresses to extremes far beyond anything found naturally on Earth. The outer layers of the star are still unaware of what is coming. They continue their fusion reactions briefly, still shining, still appearing calm from a distance. This delay is one of the most haunting aspects of stellar death. A star can look peaceful, even as its core is failing. From light years away, an observer might see nothing unusual at all. The star continues to glow, unchanged in brightness. No warning is visible. No sign reaches space until the final moment arrives. When that moment does come, it comes decisively. The collapsing core reaches a critical density and suddenly stops. The inward fall rebounds. A shockwave forms and races outward through the star's layers at incredible speed. This is the beginning of a supernova, but that story belongs to the next part. For now, it is enough to understand that supernovas are not sudden accidents or random bursts of violence. They are the result of a long, quiet life lived in balance, followed by a gradual loss of stability that cannot be reversed. Every supernova is preceded by millions or billions of years of calm light. Every explosion is born from stillness. As you rest and listen, imagine these distant stars shining steadily across the universe. Most will never explode in your lifetime. Many have already ended, their light still traveling through space long after their death. Somewhere, right now, a star is collapsing silently, unseen and unheard. Its final light has not yet begun its journey. And when it does, it will tell a story that began long before humans ever looked up at the night sky. In the next part, we will move closer to that moment, into the slow and inevitable collapse that transforms a quiet star into one of the most powerful events in the universe. After a star has spent most of its life in balance, shining steadily and quietly, it enters a phase that is far less visible, but far more consequential. This is the long decline, a period where nothing appears dramatic, yet everything is slowly changing. From a distance, the star still looks calm. Its light continues to reach space in a steady flow. To any observer watching from far away, there is no obvious sign that a star is moving toward its final transformation. But inside, the conditions that once supported stability are beginning to erode. At the heart of the star, hydrogen has already been mostly consumed. Fusion continues, but now it occurs in layers rather than in the core itself. The center contracts under gravity, growing hotter and denser as it compresses. Surrounding this core, shells of hydrogen and helium burn in sequence, each one producing energy for a time before exhausting its fuel. This layered structure is not chaotic. It is orderly, methodical, and slow. Each fusion shell ignites only when the conditions are exactly right. Pressure, temperature, and density adjust with remarkable precision, guided entirely by physical laws that never rush and never pause. As the core contracts, the star expands outward. Its outer layers swell, sometimes to many times their original size. A star that once appeared compact may now grow so large that, if placed at the center of our solar system, it could extend beyond the orbit of Mars or even Jupiter. Despite this enormous expansion, the star's surface cools. Its light shifts toward redder wavelengths, giving rise to the red giants and red supergiants scattered throughout the galaxy. These stars glow softly, often appearing dimmer than their earlier forms, even though they are vastly larger. This stage can last a very long time. For stars similar in mass to the Sun, the red giant phase unfolds slowly over hundreds of millions of years. The star gently sheds material into space, losing its outer layers in a gradual and peaceful way. These stars will never become supernovas. Their endings are quieter, fading into white dwarfs surrounded by drifting shells of gas. But for stars much more massive than the Sun, the story is different. Massive stars burn through their fuel at an extraordinary rate. The greater the mass, the stronger the gravitational pull, and the harder the star must work to resist collapse. As a result, massive stars live fast and intensely. They may shine brilliantly for only a few million years, a brief moment on cosmic timescales. In these stars, the decline accelerates. After helium fusion ends, the core contracts again. Temperatures rise to hundreds of millions of degrees. Carbon begins to fuse, then oxygen, then neon. Each stage lasts less time than the one before. What once took millions of years now takes thousands. What took thousands now takes years. The star is racing toward a limit it cannot escape. As heavier elements form, the core becomes increasingly rigid and dense. Fusion reactions release less energy with each step, providing diminishing support against gravity. The star compensates by increasing temperature, forcing reactions to continue as long as possible. But there is an absolute boundary. When iron begins to accumulate in the core, the star has reached the end of the path. Iron does not release energy when fused. It acts as a dead weight at the center of the star, growing heavier with every passing moment. At this point, the core is supported not by fusion, but by a fragile quantum pressure produced by electrons. This pressure resists gravity only up to a certain mass. As iron builds, that limit approaches. Still, the star remains outwardly calm. Light continues to travel through space. From afar, nothing signals urgency. Even nearby planets, if any exist, would experience no immediate change. Time flows normally. The star's surface glows, as it has for ages. Inside, however, gravity is winning. The iron core grows larger and denser until electron pressure can no longer hold it up. In a fraction of a second, the core collapses. Matter falls inward at a significant fraction of the speed of light. Temperatures soar beyond billions of degrees. This collapse happens faster than the rest of the star can respond. For a brief moment, the outer layers continue their fusion reactions, unaware that the core beneath them has failed. This delay is one of the most profound features of stellar death. A star can appear unchanged even as its center is already lost. Then the collapse reaches its limit. The core compresses until atomic nuclei are packed tightly together. Neutrons form in vast numbers. The inward fall halts abruptly, and the core stiffens, almost instantly. This sudden stop sends a shockwave outward. At first, the shockwave struggles. It loses energy as it pushes through dense material. For a short time, the fate of the star hangs in balance. Whether the explosion succeeds or fails depends on subtle interactions involving neutrinos, nearly massless particles that flood outward from the collapsing core. These neutrinos deposit energy into the surrounding layers, reviving the shock wave and driving it outward with unstoppable force. In less than a second, the star transitions from quiet decline to violent release. The outer layers are torn apart and hurled into space. Energy pours outward in a blinding flash. The star, which may have existed peacefully for millions of years, is destroyed in moments, but the destruction is also a beginning. The material ejected by the explosion carries with it the elements forged deep within the star: carbon, oxygen, silicon, iron, and many others. These elements scatter into interstellar space, enriching the galaxy and seeding future generations of stars and planets. Everything solid that exists today owes something to these events. The calcium in bones, the iron in blood, the silicon in rocks. All were created in stars that lived long, quiet lives before ending in supernovas. As you listen and rest, imagine this process unfolding slowly and patiently across the universe, not as a sudden catastrophe, but as the natural conclusion of a long and steady journey. In the next part, we will move into the moment itself, the collapse, the rebound, and the explosion that briefly outshines entire galaxies and marks the final transformation of a massive star. There is a point in the life of a massive star when patience ends. Not suddenly, not dramatically at first, but decisively. For millions of years, gravity has pressed inward while nuclear reactions pushed back. This balance shaped the star's entire existence. But once iron dominates the core, that balance becomes impossible to maintain. No new source of energy can be found. No reaction can restart the outward pressure. From this moment onward, the outcome is fixed. The core begins to collapse under its own weight. What had once been supported by fusion and quantum pressure now falls inward freely. Matter accelerates downward, faster and faster, compressing into a smaller and smaller volume. In less than a second, the core shrinks, from a region thousands of kilometers wide to something only tens of kilometers across. This collapse is silent in space. No light escapes faster than the collapse itself. No warning travels outward. The star's surface still shines calmly, unaware of the catastrophe unfolding deep within. Inside the collapsing core, conditions become extreme beyond comprehension. Temperatures climb into the billions of degrees. Electrons are crushed into protons, forming neutrons and releasing an immense flood of neutrinos. Atoms no longer exist as recognizable structures. Matter becomes something closer to pure density. Gravity continues to pull inward, relentless and absolute. Then, at a critical point, the collapse stops. The core reaches a density so high that neutrons themselves resist further compression. This resistance is sudden and firm. The inward motion halts almost instantly, like an object striking an immovable surface. The result is a rebound. The inner core snaps back slightly, sending a powerful shock wave outward into the still collapsing outer core. This shock wave is the first physical sign that a supernova is about to occur. It moves outward at enormous speed, plowing through layers of dense matter that were moments ago falling inward. At first, the shock wave struggles. The surrounding material absorbs energy, weakening the wave. Heavy atomic nuclei break apart under the intense heat, draining even more energy from the shock. For a brief and critical moment, the explosion nearly fails. This pause lasts only fractions of a second, yet it determines the fate of the star. From the newly formed neutron core, an overwhelming number of neutrinos stream outward. These nearly massless particles pass through matter easily, but not entirely without interaction. A small fraction of them deposit energy into the region just behind the shock wave. That energy is enough. The shock wave strengthens, regains momentum, and surges outward once more. Gravity can no longer hold the star together. The outer layers reverse direction and are violently expelled into space. In that instant, the supernova begins. Light erupts outward, racing ahead of the expanding debris. For a short time, the dying star can shine brighter than an entire galaxy. From across the universe, this flash can be seen as a new point of light where none existed before. Yet even this brilliance is brief. Within days or weeks, the initial glare fades. What remains is a vast cloud of expanding gas, glowing softly as it cools and disperses into space. The star, as it once was, is gone forever. At the center of this expanding cloud lies the remnant core. Either a neutron star, or if the original star was massive enough, a black hole. This remnant holds the compressed remains of the star's heart, dense beyond imagination, silent and enduring. Everything beyond it continues outward, carrying the star's material across light years of space. This is not destruction alone. The explosion triggers reactions that cannot occur anywhere else. In the brief, violent conditions of a supernova, elements heavier than iron are created: gold, platinum, uranium. These atoms are scattered into the galaxy, becoming part of future stars, planets, and eventually life. The moment the core gives way is both an ending and a beginning. A star that lived quietly for millions of years ends in less than a second. Yet the influence of that second echoes for billions of years afterward. As you rest, imagine this moment not as violence, but as release. A long-held structure finally letting go, returning its substance to the universe from which it came. In the next part, we will explore what remains after the explosion, the dense remnants left behind, and the expanding shells of matter that reshape the space around them. When the light of a supernova begins to fade, the most dramatic moment has already passed. The flash that briefly outshines galaxies softens, and the expanding debris slows as it moves outward into surrounding space. What remains is quieter, more subtle, yet no less important. This is the afterlife of a star. The material once held together by gravity now drifts away in all directions. Vast clouds of gas and dust expand into the darkness, glowing faintly as they cool. These expanding shells, known as supernova remnants, can grow to span dozens or even hundreds of light years over time. From a distance, they appear as delicate, filament-like structures, wisps of light against the blackness of space. Their shapes are sculpted by shock waves, magnetic fields, and the uneven density of the surrounding interstellar medium. No two remnants are exactly alike. Within these expanding clouds lie the elements forged during the star's lifetime and final moments. Carbon, oxygen, silicon, iron, and heavier elements created in the explosion itself are carried outward, mixing with the gas between stars. Over millions of years, this material becomes part of new star-forming regions, continuing the cycle. At the very center of the remnant, something compact and extraordinary remains. If the original star was massive, but not overwhelmingly so, its core survives as a neutron star. This object is incredibly dense. A mass greater than that of the Sun is compressed into a sphere only about 20 kilometers across. Matter here exists in a form not found anywhere else in the universe. Neutron stars are born spinning rapidly. As the core collapses, conservation of angular momentum causes it to rotate faster, sometimes hundreds of times per second. Strong magnetic fields are trapped within the star, becoming trillions of times stronger than Earth's magnetic field. Some neutron stars emit beams of radiation from their magnetic poles. As they spin, these beams sweep through space like lighthouse beams. When aligned with Earth, they are observed as pulsars, precise, rhythmic signals, arriving with astonishing regularity. If the star that exploded was even more massive, gravity overwhelms all resistance. The core continues collapsing beyond the neutron star stage, forming a black hole. In this case, no solid surface remains. The core disappears behind an event horizon, sealing itself off from the rest of the universe. Both outcomes are extreme. Both represent matter pushed to its absolute limits. Around these remnants, the expanding supernova debris continues to interact with space. Shock waves compress nearby gas, sometimes triggering the collapse of clouds that will eventually form new stars. In this way, a supernova can both end and begin stellar lives. This process unfolds slowly. Thousands of years after the explosion, the remnant still glows faintly. Tens of thousands of years later, it becomes more diffuse, blending gradually into the background of the galaxy. Eventually, its distinct structure disappears, but its material remains, fully mixed into the cosmic environment. Nothing is wasted. The atoms that once formed the core of a massive star may someday become part of a planet, an ocean, or a living organism. The universe recycles its material endlessly, reshaping it across unimaginable spans of time. As you listen, imagine these remnants drifting quietly through space. The violence is long past. What remains is calm expansion, gentle motion, and slow integration into the larger whole. In the next part, we will step back and explore the different kinds of supernovas, how stars of different masses and histories reach similar endings through distinct paths. Not every supernova is born in the same way. While the explosion itself may look similar from a distance, a sudden brightening of light followed by a fading glow. The journey toward that moment can be very different. The universe allows more than one path to reach the same extraordinary conclusion. Some stars die alone, others die because of a companion. To understand these different endings, we move away from the remnants and return once more to the lives of stars themselves. Many stars do not exist in isolation. Across the galaxy, a large number are part of binary systems, pairs of stars bound together by gravity, orbiting a shared center. These stellar companions can remain together for millions or billions of years, quietly influencing each other in subtle ways. In certain systems, this companionship changes everything. One of the most important alternative paths to a supernova begins with a small, dense star known as a white dwarf. A white dwarf is the leftover core of a star that was once similar in size to the Sun. After shedding its outer layers, the star leaves behind a compact object, roughly the size of Earth, supported by quantum pressure rather than fusion. On its own, a white dwarf is stable. It cools slowly. It fades quietly. But if a white dwarf orbits close to another star, the situation becomes far more delicate. As the companion star evolves and expands, its outer layers can drift toward the white dwarf. Gravity pulls this material across the gap between them, forming a stream of gas that spirals inward. Over time, the white dwarf begins to gain mass. This process is slow and steady. Hydrogen accumulates on the white dwarf's surface, compressing under intense gravity. When enough material gathers, fusion ignites in a sudden flash, creating a nova, a brief but relatively modest outburst. Afterward, the white dwarf remains intact, ready to begin the process again. But this cycle cannot continue forever. There is a critical mass limit that a white dwarf cannot exceed. As it grows heavier, the pressure supporting it becomes less effective. Once this limit is crossed, stability vanishes. Unlike massive stars, the white dwarf does not collapse into a neutron star. Instead, something different happens. The entire star ignites. Carbon fusion begins throughout the white dwarf almost simultaneously. There is no layered structure, no gradual collapse. In a fraction of a second, nuclear reactions race through the star, releasing an immense amount of energy. The white dwarf is completely destroyed. This type of explosion is known as a thermonuclear supernova. No remnant remains. Nothing survives at the center. The star is erased entirely, leaving behind only an expanding cloud of debris. These explosions are remarkably consistent. Because they occur at nearly the same mass each time, their brightness is predictable. This makes them invaluable to astronomers, who use them as cosmic distance markers to measure the scale of the universe. Despite their scientific importance, the process itself is calm and inevitable, driven by quiet mass transfer over immense periods of time. Elsewhere in the universe, another path unfolds. Massive stars, born with many times the mass of the Sun, live fast and intensely. Their fuel burns quickly. Their internal pressures are enormous. Their lives are brief by cosmic standards. These stars follow the path we explored earlier. Layered fusion, iron cores, gravitational collapse. When their cores fail, the explosion that follows tears them apart while leaving behind a dense remnant. This is the most familiar image of a supernova. A massive star collapsing inward, rebounding outward and scattering its substance across space. Though the mechanisms differ, the outcome is similar. Energy is released on an unimaginable scale. Matter is expelled into the galaxy. Elements essential to future stars and planets are distributed far and wide. Different paths, same cosmic role. What is most striking is how quiet these processes are until the very end. For millions of years, stars change gradually, patiently, without spectacle. Only when physical limits are reached does the universe allow release. There is no urgency, no warning, only inevitability. As you listen, imagine countless stars across the universe approaching their endings along different routes. Some gather mass from companions, some burn alone, some collapse inward, some ignite all at once. All of them contribute to the same ongoing story, a universe constantly reshaping itself through cycles of calm creation and gentle destruction. In the next part, we will slow the pace even further and look at how these explosions appear from afar, how their light travels across space, and how humans have observed and recorded supernovas throughout history. When a supernova occurs, the explosion itself is already over before its story truly begins. The collapse, rebound, and release of energy happen in moments, deep within a distant galaxy. But what reaches the rest of the universe is something far gentler. Light, spreading outward at a constant pace, carrying information across unimaginable distances. This light does not rush, it simply travels. From the site of the explosion, photons move outward in every direction, passing through expanding clouds of debris, drifting into interstellar space, and continuing onward through the quiet darkness between stars. Some of this light will never encounter anything at all. It will move forever, thinning into the vastness of the universe. Other portions of that light will eventually reach planets, telescopes, and eyes. When humans observe a supernova, they are never seeing it as it is now. They are seeing it as it was, sometimes thousands, millions, or even billions of years ago. The explosion may have already faded into a remnant long before its light arrives. In this way, every supernova observation is an act of looking into the past. A star could explode in a distant galaxy tonight, and no signal of that event would reach Earth for millions of years. Civilizations may rise and fall before the light ever arrives. Continents may shift, oceans may vanish, and yet the photons will continue on, unchanged, indifferent to what happens along the way. When that light finally reaches Earth, it appears suddenly. A point in the sky brightens where none existed before. Over days or weeks, it grows more luminous, sometimes becoming visible even to the naked eye. Then slowly it fades. This slow fading is important. As the debris cloud expands, it cools. Energy spreads out. The intense brightness softens into a gentle glow, then into faint traces, visible only through careful observation. The universe gives no sharp ending to the display. It simply allows the light to diminish naturally. Throughout history, humans have noticed these sudden stars. Long before telescopes, observers recorded unfamiliar points of light appearing in the sky, lingering for months, then disappearing. Without knowledge of stellar evolution, these events were mysterious and often unsettling. They challenged the idea that the heavens were perfect and unchanging. Some ancient observers described them as guest stars, temporary visitors to a sky that was otherwise stable and eternal. What they were truly witnessing was death on a cosmic scale. Yet even in death, the message carried by a supernova is not one of chaos, but of continuity, The light that reaches Earth contains signatures of the elements formed in the explosion. By studying this light, astronomers can identify the materials expelled into space, reading the chemical story of the star's final moments. Every spectrum is a quiet record, every wavelength a gentle clue. As you rest, imagine this light traveling calmly across space, uninterrupted by time or distance. A silent message moving steadily toward wherever it may be received. In the next part, we will explore how these distant explosions have shaped galaxies themselves, influencing star formation, structure, and the long evolution of cosmic systems. Long after the brilliant light of a supernova fades from view, long after the expanding cloud becomes faint and diffuse, the influence of that single event continues quietly. The universe does not rush past these explosions. It absorbs them slowly, allowing their effects to unfold over immense stretches of time. Galaxies are not static collections of stars frozen in place. They are slow, dynamic systems made of gas, dust, stars, and unseen matter, all bound together by gravity and motion. Within them, nothing remains truly still. Even regions that appear calm are part of larger flows that extend across tens of thousands of light years. Supernovas are among the most important forces shaping these flows. When a star explodes, it releases an enormous amount of energy into its surroundings. This energy does not vanish after the flash of light fades. Instead, it moves outward as expanding shock waves, pushing into the interstellar medium. The thin, nearly invisible mixture of gas and dust that fills the space between stars. Under normal conditions, the interstellar medium is quiet and cold. Gas atoms drift slowly. Dust particles float gently, influenced only by weak magnetic fields and distant gravity. These regions can remain unchanged for millions of years, stable and uneventful. A supernova changes that balance. As the shock wave travels outward, it compresses the gas ahead of it. Density increases, pressure rises. Regions that were once too diffuse to collapse suddenly cross a threshold. Gravity begins to act more efficiently, pulling matter inward. This compression does not create stars immediately. Instead, it sets the stage. Over hundreds of thousands of years, compressed gas clouds cool and fragment. Small pockets grow denser than their surroundings. These pockets slowly collapse, spinning as they fall inward. Temperatures rise gradually, and eventually new stars ignite at their centers. In this way, a supernova can influence star formation long after the explosion itself has ended. The star that exploded may be long gone, but its pressure wave continues to guide where and when new stars appear. Entire clusters of stars can trace their origins back to ancient explosions that occurred millions of years earlier. This process is subtle, patient, and widespread. Supernovas do not create chaos within galaxies. They create rhythm. They also prevent galaxies from evolving too quickly. Without energetic feedback, gas within galaxies would collapse efficiently under gravity. Stars would form rapidly and in large numbers, consuming available material in a relatively short time. Galaxies would burn brightly, then fade, leaving behind aging stellar populations with little capacity for renewal. Supernovas slow this process. By injecting energy into the surrounding gas, they heat it and keep it in motion. Hot gas resists collapse. It spreads out, rises above galactic disks, and cools only slowly. This delay ensures that star formation occurs gradually rather than in short, intense bursts. This balance is essential for long-lived galaxies. Too little supernova activity, and star formation becomes runaway. Too much, and gas is driven away entirely. Most galaxies exist in a narrow middle ground, maintained by the rare but powerful influence of exploding stars. Supernovas also act as the primary distributors of heavy elements. At the beginning of the universe, only the lightest elements existed. Hydrogen and helium filled space almost uniformly. Everything heavier was created later inside stars. But creating these elements is only part of the story. They must also be spread. Without supernovas, heavy elements would remain locked inside stellar cores or quietly settle into compact remnants. Galaxies would remain chemically uneven, with primitive regions and enriched regions isolated from one another. Supernova explosions solve this problem. As remnants expand, they mix stellar material into the surrounding medium. Shock waves stir gas across vast regions, blending elements and smoothing chemical differences. Over billions of years, this mixing ensures that new stars form from increasingly enriched material. Each generation inherits more complexity than the last. This gradual enrichment changes the nature of what can exist in the universe. Rocky planets require silicon, iron, and magnesium. Water depends on oxygen. Atmospheres depend on nitrogen and carbon. Complex chemistry relies on the availability of many elements working together. All of these depend on supernovas. In spiral galaxies, these processes are especially visible along spiral arms. Massive stars form in these dense regions, live short lives, and explode near where they were born. The spiral arms glow softly with nebulae, young stars, and the lingering remains of older explosions layered together. The arms themselves persist because star formation is regulated rather than exhausted. Supernovas help maintain this balance, ensuring that spiral structures remain active over billions of years. In smaller galaxies, the influence of supernovas can be even more dramatic. Dwarf galaxies possess weaker gravitational holds. When massive stars explode within them, the released energy can push gas completely out of the system. Once that gas escapes, star formation slows dramatically or stops altogether. Some dwarf galaxies experience only a few generations of star formation before becoming quiet and faint. Their evolution is shaped almost entirely by how effectively they retain or lose gas after supernova explosions. Across the universe, the combined influence of countless supernovas shapes galactic evolution on the largest scales. Galaxies acquire structure, chemical complexity spreads, and the conditions for planets and life become more common. None of this happens quickly. Supernovas are rare events, separated by long periods of calm. Their power lies not in frequency, but in consequence. A single explosion can influence regions of space for millions of years, long after its light has faded. As you rest, imagine a galaxy turning slowly in the darkness. Within it, stars shine quietly, unaware of the ancient explosions that shaped their environment. Shockwaves from long-dead stars continue to move invisibly through space, compressing gas, mixing elements, and preparing the ground for futures not yet written. The universe does not hurry. It builds complexity one quiet explosion at a time. In the next part, we will move closer to our own origins and explore how ancient supernovas helped shape the environment from which the sun, the earth, and life itself eventually emerged. Long before the sun existed, long before Earth formed, the region of space that would one day become our home was already shaped by events far older and far more powerful than anything humanity has ever witnessed. These events, did not happen nearby in time, but they happened nearby in space, quietly preparing the conditions necessary for everything that followed. Our solar system was not born in isolation. It emerged from a galaxy already aged, already enriched, already shaped by countless generations of stars. At the beginning of the universe, there were no rocky worlds, no oceans, no atmospheres like the ones surrounding Earth today. Space was simple. Hydrogen and helium filled vast regions almost uniformly. Complexity had not yet arrived. That complexity came later, carried outward by supernovas. Before the sun could form, before planets could assemble, the raw materials needed for such structures had to exist. Elements like carbon, oxygen, silicon, iron, magnesium, and calcium are not produced in the Big Bang. They are created inside stars and released through stellar death. This means that our origins are tied directly to stars that lived and died long before the sun ever ignited. Somewhere in the Milky Way, millions or even billions of years before Earth existed, massive stars ended their lives in supernovas. Their explosions scattered enriched material into the surrounding interstellar medium. Over time, this material mixed with gas from other regions, blending elements from many different stellar ancestors. By the time the cloud that would form our solar system began to collapse, it was no longer simple. It was rich. It was complex. It carried the quiet legacy of ancient explosions. This cloud drifted through the galaxy, cold and dark, for an immense period of time. Nothing about it suggested planets or life, but within it were atoms forged in extreme conditions, iron formed in stellar cores, oxygen produced through fusion, carbon shaped by long-lived stars and explosive endings. Eventually, something disturbed this cloud. It may have been the shock wave from a nearby supernova passing gently through the region. Or it may have been a slow, gravitational interaction with surrounding matter. Whatever the cause, part of the cloud began to collapse inward. As it did, gravity took control. Material fell toward the center, forming a dense, rotating disk. At the heart of this disk, pressure and temperature increased until nuclear fusion ignited. A new star was born, the Sun. Around it, within the flattened disk of gas and dust, planets began to form. The inner regions of the disk, rich in heavy elements, produced rocky worlds. Iron and silicon clumped together. Dust grains collided, stuck, and slowly grew into larger bodies. Over millions of years, these bodies became planets. Earth formed from this process. Every atom of iron in Earth's core, every grain of silicon in its crust, every trace of calcium in its rocks originated in stars that lived and died long before our planet existed. These materials did not form here. They arrived already prepared, carried across space by supernovas. Even the oxygen in Earth's oceans and atmosphere owes its existence to stellar processes. Without ancient explosions, there would be no water as we know it, no breathable air, no stable surface for life to emerge. In this sense, Earth is a product of many deaths. Not violent deaths remembered by light, but quiet contributions spread across time. Each supernova added a small piece to the material that would eventually gather into worlds. Some evidence of this history remains. Scientists have found traces of radioactive elements in ancient rocks on Earth, elements that decay over known timescales and are associated with supernova production. These traces suggest that one or more supernovas occurred relatively close to the region where the Sun formed, not close enough to destroy the forming solar system, but close enough to influence it. These explosions may have helped trigger the collapse of the solar nebula itself. They may have delivered short-lived radioactive elements that warmed early planetary bodies, driving internal heating and differentiation. In other words, supernovas may have shaped not just the material of Earth, but its early evolution. As the young Earth cooled, its heavy elements sank inward, forming a dense core. Lighter materials rose to the surface. Volcanic activity released gases, forming an atmosphere. Water collected. Chemical complexity increased. None of this would have been possible without the raw materials delivered by ancient stellar explosions. Life itself is built from these elements. Carbon forms the backbone of organic molecules. Oxygen enables complex chemistry and energy exchange. Nitrogen stabilizes proteins and genetic material. Phosphorus plays a central role in cellular processes. All of them came from stars. As you rest, imagine the long chain of events that connects distant supernovas to life on Earth. Imagine explosions that occurred long before the sun existed. Their light long faded, their remnants dispersed, yet their material still present. Here, now, within everything solid and living. Nothing about this process was rushed. Nothing was planned. It unfolded naturally, patiently, across billions of years. In the next part, we will look beyond Earth once more and explore how supernovas may influence the future, how stars yet to explode will continue shaping galaxies, worlds, and possibilities far beyond our own time. The story of supernovas does not end with the past, and it does not pause in the present. Even now, across the universe, stars are quietly approaching the final stages of their lives. Their futures are already written in their mass, their composition, and the slow, unchanging laws that govern them. What remains unknown is only the timing. Somewhere in the Milky Way tonight, massive stars are burning through the last portions of their fuel. They shine steadily, giving no outward sign of urgency. To any distant observer, they appear calm and unchanged. Yet deep within their cores, conditions are evolving toward collapse. The universe is patient, but it is never idle. In the far future, supernovas will continue to shape galaxies, much as they always have, though the environment in which they occur will slowly change. As galaxies age, their gas supplies diminish. Star formation becomes less frequent. Massive stars become rarer. Supernovas, once common in youthful galaxies, occur more sparsely. This gradual quieting is not sudden. It unfolds over tens of billions of years. As star formation slows, galaxies shift from active systems filled with glowing nebulae to quieter collections of aging stars. In these later eras, supernovas become rare events, isolated flashes separated by immense stretches of time. Yet even in this quieter universe, their influence remains meaningful. Each future supernova will still inject energy into its surroundings, stirring gas, redistributing elements, and subtly reshaping its local environment. Even a single explosion can alter the fate of nearby clouds, triggering or suppressing star formation depending on conditions. Supernovas are not concerned with eras. They act whenever the conditions allow. In regions where galaxies collide or merge, new bursts of star formation can occur, even in an aging universe. Gas is compressed. Massive stars form once more. And with them comes the return of supernovas. Brief, powerful reminders that the universe still possesses the capacity for change. Over even longer timescales, the role of supernovas will slowly diminish. as hydrogen becomes scarcer and star formation declines further, fewer massive stars will be born. White dwarfs will still exist, and some will continue to explode through thermonuclear processes, but these too will become less frequent as binary systems evolve and exhaust their interactions. Eventually, the universe will enter an era dominated by long-lived, low-mass stars. These stars burn their fuel slowly, quietly, and efficiently. Many will never explode at all. They will fade gently into compact remnants, leaving behind little disruption. The age of frequent supernovas will pass, but even then, their legacy will remain everywhere. The elements produced by past explosions will persist, locked into stars, planets, and remnants. Every rocky world that still exists in those distant eras will owe its structure to ancient supernovas long extinguished. Every molecule of water, every mineral grain, every trace of heavy chemistry will carry the imprint of explosions that occurred billions of years earlier. Supernovas shape not just environments, but possibilities. Without them, complexity cannot arise. Without them, the universe remains simple and quiet. In this sense, supernovas represent a bridge between eras, a mechanism by which the universe transforms itself from simplicity to richness, from uniformity to structure. They are moments when accumulated energy and matter are released back into the wider system, ensuring that no generation of stars exists in isolation. Between one supernova and the next, there is an immense silence. This silence is not emptiness. It is filled with slow motion, gentle forces, and time unfolding at a pace far beyond human awareness. Galaxies drift, stars shine steadily, gas clouds move almost imperceptibly through space. Nothing appears to demand attention, and yet everything is slowly changing. Most of the universe exists in this in-between state. Supernovas are rare. Even in large galaxies, they occur only occasionally, separated by decades, centuries, or longer. On cosmic timescales, they are brief punctuation marks in long, continuous sentences written by gravity and time. The universe spends far more time preparing for explosions than experiencing them. Stars live quietly for millions or billions of years. They shine without urgency. Their internal reactions proceed steadily, guided by unchanging physical laws. From the outside, nothing suggests drama or instability. This long calm is the dominant state of cosmic existence. It is easy to focus on the explosion and forget the silence that surrounds it. Yet that silence is where structure forms. Gas slowly gathers into clouds. Dust grains collide and stick. Magnetic fields guide motion in subtle ways. Over vast spans of time, these gentle processes shape galaxies just as surely as the most powerful explosions. Even after a supernova, the universe returns to silence. The expanding remnant slows, its edges soften. Energy dissipates. What was once a brilliant event becomes a faint whisper of motion, gradually blending back into the background. Eventually, even that whisper fades, leaving only slightly altered conditions behind. This return to quiet is not a failure of drama. It is the universe restoring balance. In this silence, remnants drift without purpose. Neutron stars cool and spin more slowly. Black holes wait without movement, responding only when matter wanders too close. The heavy elements created in the explosion settle into the interstellar medium, indistinguishable from material that has been there for ages. Nothing announces that something extraordinary once occurred, and yet everything remembers. Every region of space carries the accumulated history of countless past events. density, temperature, composition, all are shaped by what came before. Even silence has a memory. As you rest, imagine the universe not at the moment of explosion, but long afterward. Imagine space returning to stillness, motion slowing, light fading. This is not an ending. It is a continuation, quiet, patient, and stable. The universe prefers this state. Explosions are necessary, but silence is home. In this long calm, new possibilities form. New stars begin their slow lives. New systems take shape. Everything that will one day change is already quietly becoming something else. And so the universe waits, unhurried, untroubled, until the next star, somewhere far away, reaches its limit and releases what it has been holding. Until then, there is only time. If there is one lesson written into the structure of the universe, it is this: nothing is meant to remain unchanged forever. Stars form, shine, and eventually release themselves back into space. Galaxies grow, evolve, and slowly quiet. Even the universe itself expands continuously, never returning to a previous state. Supernovas are one expression of this larger truth. They are moments when the universe lets go of what it has carefully built, not out of destruction, but necessity. A star reaches a limit it cannot cross. Holding on is no longer possible. Release becomes the only path forward. This pattern repeats everywhere. Gas clouds collapse until pressure ignites fusion. Fusion continues until fuel runs low. Balance holds until it cannot. At each stage, change comes not from choice, but from inevitability. There is no resistance in this process, no struggle, only transition. Supernovas remind us that endings are not failures. They are transformations that allow complexity to continue rather than stagnate. Without release, stars would trap material forever. Without redistribution, galaxies would lose the ability to renew themselves. Letting go is how the universe survives. Even on the largest scales, this principle holds. As time passes, energy spreads out. Motion becomes gentler. Differences smooth away. The universe slowly moves toward quiet. Not suddenly, not dramatically, but steadily. And still, within that quiet structure remains possible because of what supernovas have already done. The atoms that form planets, oceans, and living things are not accidents. They are the result of repeated cycles of holding and releasing, building and dispersing, shining and fading. Everything solid has passed through fire. Everything complex has survived collapse. As you drift deeper into rest, consider this vast patience. The universe does not rush toward its future. It allows each stage to complete fully before moving on. Nothing is forced, nothing is wasted. Somewhere, far beyond any place that can be reached, stars are quietly preparing to end. Somewhere else, new stars are beginning their long lives, made possible by ancient endings. All of this is happening at once, layered across time. There is no final explosion, no ultimate silence, only an endless sequence of gentle transitions. And so this journey does not truly end here. Like a supernova's fading glow, it simply softens, becoming part of a larger stillness. The universe continues, patient and unhurried, carrying forward everything it has ever been. And you, listening now, are part of that same story. Made of ancient stars, shaped by long past explosions, resting within the quiet that follows. Everything continues,